In this video, we want to continue to look at definite integrals, but today we're going to look at some properties of definite integrals and to kind of help us as we try to evaluate them. First, consider this integral from 1 to 5 of 4x plus 1. Now, from what we did in the last section, we could talk about our delta xk is b minus a over n, so this would be 4 over n. Our c sub k is a plus k times delta x. And we could go through all of that and plug that in and do our Riemann sum. But in this situation, I want to talk about this from a little different angle that we're going to look at today. Think about what this is. If I was to graph this, I'm looking at the area from 1 to 5 of a line, not necessarily to scale, of that line. And so I'm looking for this area right here. And if you think about it, we could take that area and we could break this into this rectangle and then this triangle. So if we found those two areas, we would be able to find this integral not by using the limit of our Riemann sum, but by just using our areas. So sometimes if this function is just a line, something that we can easily use area function for, we can find the answer by just finding the area. So that's one thing we'll be looking at as we go forward. The other thing we're going to look at today are our properties of definite integrals. And these properties will help us as we evaluate these integrals. So our first property, property number 1, is if you reverse the limits, the integral from a to b of f of x dx, and we change it to the integral from b to a of f of x dx, what that does is that reverses the sign and it makes it negative. So if you think about that from our rectangles that we've looked at previously, what that would do is, if you think back to our RAM rule, right? And if we have 1 to 2 and we're trying to find that area, right? And let's say we have that rectangle right there, right? We would have this, and then we would say that would be 2 minus 1 to find the area. If we switch the limits, what that would do is it would change this to 1 minus 2. So all that would do is it would change our answer by making this a negative instead of a positive. So that's our first property. Our second property is if the upper and lower limit are the same, then this integral is just 0, which once again makes sense. If you think about this from a picture if we want to find the integral from 3 to 3, there is no area under the curve. That's 0. That's all that this property is telling us. Our third property tells us if we have a constant in our function, in front of our function, we can move that k outside of our function and then just evaluate the integral and multiply by the k. And if you think about it, our integral is defined based on limits. So that's our rule with limits. That was our rules with sigma. All of those things are similar. We took derivatives. You can move a constant multiple out. Our fourth property says if you have an addition, you basically can split that into 2 integrals instead of just 1. Once again, that kind of makes sense. If you think about it, if we go to our picture, if I get rid of this, right? If we have the integral from 1 to 2, and we have two parts of it, we can just add those together. Our fifth property is a little different. This says if we have the integral from a to b and an integral from b to c, we can combine that into a single integral from a to c. Now, if we think about that from the graph, this makes complete sense. If we have the area from a to b, and then we have the area from b to c, we could combine those into one integral. However, there's a very interesting thing about this part b. It doesn't actually have to be between a and c. Let me show you what I mean by that. So let me go back, go here. So let's say we have a to b, and we are trying to find, or we're talking about this area, right? So this would be the area of a to b of f of x dx. Now, let's split this up to some value c way out here. Now, that doesn't seem like that's anywhere associated to it, but I could rewrite this as a to c of f of x dx plus the integral from c to b of f of x dx. And that's just following our property here. Doesn't say anything about where those a's and b's and c's have to be. And if you think about this integral here from, let me switch colors, this integral here from a to c is this area right here. This integral from c to b is this area right here. But if you notice, c is the bigger number, which means the way this integral, the way this integral is written, this will actually be minus the area because the limits are switched from the way that they should be. So that means that this blue area will actually be subtracted from the green area, which gives you the red area. So the point is that value c doesn't even have to be between the two values for this property to still work. Okay, so let's use these properties to evaluate some integrals. So let's say we are given that from -1 to 2 of f of x dx is 5, 2 to 5 of f of x is 6, and -1 to 2 of h equals 4. We want to use those four properties to evaluate this integral. So we want the integral from -1 to 5. We don't have the one from -1 to 5, but I can rewrite this as -1 to 2 of f of x dx plus the integral from 2 to 5 of f of x dx, which is just going to give me 5 plus 6, which is 11. If I have the integral of -1 to 2 of h of x over 2 dx, that over 2 is 1/2. I can just pull it out in front. Now my integral from -1 to 2 of h is just 4. So I can get 2. And my last one is from -1 to 2 of f and h. So I can split this into two separate integrals. And my integral of f of x is 5, h is 4. So this would be 5 plus 4 equals 9. So that's just some practice of how we could use those properties. Let's try a couple more. We are given that the integral from 0 to 2 of x squared dx is 8/3. So what would be the integral from 2 to 0 of x squared dx? Well, To use the top one, I could say this would be minus, and I can change my limits, and this would just be minus 8/3. If I have the integral from 0 to 2 of 4x squared, this 4 is a constant multiple, so I can pull that out in front and do 0 to 2 x squared dx. That's 4 times 8/3, which would give me 32/3. So those are some examples of how we can use those properties. Let's try some more. What if we have the integral from 0 to 2 of x squared plus 1? Well, we can split this into 2x squared dx plus 0 to 2 of 1 dx. This is 8/3. This integral here, we can just think about that, right? If we were to graph that, that is the line at 1, 0 to 2, it's just that rectangle, which is just 2, which would be 6/3. So that's 14/3. Another one. Once again, we can split this into 2, and the first one, we could take the 3 out in front, minus the integral from 0 to 2 dx. This is 3 times 8/3 minus, similar one here, this is 0 to 2. That is just 4. So that gives us just 4. So these are examples of how we can just use these properties sometimes to simplify an integral down to something maybe we already know or something that's easier to evaluate. Now, one of the things I want to mention with all of our integrals is the idea of dummy variables. And what does that mean? Well, we just said if we have the integral from 0 to 2 x squared dx, that is 8/3. The important thing to understand, when you do this integral, I could say this is the integral from 0 to 2 of t squared dt. That's still 8/3. I could say this is the integral from 0 to 2 of theta squared d theta. That is 8/3. I could say this is the integral from 0 to 2 of y squared dy. And that is 8/3. When we are finding these integrals, and we're doing this, the actual variable in the integral doesn't matter. It's called a dummy variable. You just put any variable can be there and you still get the same exact integral. Now, almost most of the time, we do it with x. That's just the variable we're used to, but it doesn't have to be x. So let's look at another example. Find the total area of x minus 1 on 0 to 3. So here's our graph. So we have 2 triangles. Now, if we just found, or let's find the area of our 2 triangles, this is 2 by 2. So this whole area is 2. This area is 1 by 1. So this is -1/2. If we would write this as, what's the integral from 0 to 3 of x minus 1 dx, that would be 1.5. Because this area that is below the x-axis, this -1/2, would be a negative value and would take away from our total. Now, in this question, it actually asks for the total area. So it wants the total area. So to find the total area, what we have to do is we have to split this into 2 integrals. We're going to integrate, this is 1 here. we're going to integrate from 0 to 1, x minus 1 dx, plus 1 to 3, x minus 1 dx. But the thing we know from just kind of looking at the graph and the situation, this first part is actually a negative. So I need to put a negative in front to make it positive so that my total area is 2.5. We talked about this when we talked about the difference between displacement and distance, right? This would be displacement, where you have to deal with the positives and negatives, and total distance, you have to make everything positive. All right, that is our section 5.2 on the properties of definite integrals.